Okay, so we're going to talk about section 2.7, that's implicit differentiation. And as a motivating question, let's consider how we would find the equation of the line tangent to the curve x squared plus y squared equals 16 at the point 2, 2. So something to point out first of all is this equation x squared plus y squared equals 16, that's the equation of a circle, right? And a circle is not even a function, right? This is going to be a circle with a radius of 4 centered at the origin, so this is 4. All right, here's our circle, something like this. And so this isn't a function because it fails a vertical line test, but I mean, we can still talk about the rate of change, especially if we try to sort of ignore this, maybe only look at the top half of the circle to make it a function or something like that. And at the point 2, 2, somewhere around here, we can still talk about the tangent line because we can still talk about the rate of change. But it doesn't make sense to write the equation of this curve in terms of y, because it's not really a function of y, it's not a function at all. Okay, so far everything that we've looked at, all of the functions we've taken derivatives of have been for explicit functions. So an explicit function is one in which the dependent variable y is described in terms of the independent variable x, and sometimes we change those names around, but that's all of the derivatives that we've done so far. And we know how to take these derivatives, right? If you want to take the derivative of y with respect to x here, you would get dy dx, also known as y prime, shorthand, is equal to, we'd use the power rule here to get 3x squared plus 5. And in the second case, if we want to find dy dx or y prime, the derivative of sine is cosine with respect to x, and the derivative of e to the x is e to the x. Right? These ones we know how to do already. And notice what we're doing in both cases is we're taking the derivative of each side of the equation with respect to x. But an implicit function is a little bit different. So an implicit function is a function that's described in terms of both variables, right? So for example, if we had the function x squared plus y squared equals 4, oh, sorry, it's not a function, right? If we had this equation x squared plus y squared equals 4, or even more complicated ones like x squared minus xy equals 2xy squared, right? These are curves that aren't necessarily functions, so I guess we should have said equations here, since they're not necessarily functions. We can still talk about the rate of change, we can still talk about tangent lines, but it's not as straightforward to find the slopes of those tangent lines because it's not as straightforward to find the derivatives. So for something like this, we need to use something called implicit differentiation, right? Differentiation for equations that are written implicitly. So when we use implicit differentiation, we take the derivative of an implicit equation or function, and we make use of the fact that the derivative with respect to x can be thought of as the derivative with respect to y, or some other variable, times dy dx. Right? In some sense, you can think about this denominator and this numerator sort of canceling, although that's not exactly how it works. But that's good enough sort of for our purposes to see how we would take this derivative. So in particular, if you're taking the derivative of a function that's written implicitly with both x's and y's, then you're just going to take the derivative of both sides of the equation with respect to x. And then anytime you take the derivative of a y term, you take the derivative with respect to y and then multiply by dy dx. So let me show you what I mean using our original example. All right, we want to take the derivative with respect to x on both sides. So I'm going to start just by saying we're taking the derivative with respect to x on the left-hand side, and we're taking the derivative with respect to derivative with respect to x on the right-hand side. Okay, and we know that when you're taking the derivative of two functions that are being added together, you can break it up into two separate derivatives. So we have the derivative with respect to x of x squared plus the derivative with respect to x of y squared, and that's going to be equal to the derivative with respect to x of the constant 4. Okay, the derivative of a constant is always 0, so that term's already gone. Now let's return to the left-hand side. We've got the derivative with respect to x of x squared. Easy enough using the power rule. This is 2x. But this is the harder part here. We need to take the derivative with respect to x of y squared. If we go up to the top, we see what we're supposed to do is, if our equation has a y term in it, then we take the derivative of that term with respect to y, and we multiply by dy dx, right? We're making use of this equation right here. So we'll add down here, the derivative of this with respect to y would be 2y, using the power rule again, but because we took the derivative of a y term, we also have to multiply by dy dx. Okay, so we're just using this fact up here. We're taking the derivative of a term that has a y in it, so we differentiate with respect to y, then multiply by dy dx. Now we're almost done because all we really need to do here, if we want to try to find the slope of the tangent line for this particular curve, is we solve for dy dx, right? We solve for y prime, we solve for the derivative. So to do that, we have to move our other term to the other side of the equation. So subtract 2x on both sides to get rid of it over here. And so we have 2y dy dx is equal to negative 2x. And finally, to get dy dx by itself, we would just divide by both sides by 2y to get rid of that 2y. And so we end up with the fact that dy dx, that's our y prime term, is going to be equal to negative 2x over 2y. Of course, the 2's will cancel as well, so if you wanted to, you could really write this y prime term as negative x over y. Right, so the derivative of y is going to be equal to negative x over y. So why do we care about that? Why does it help us? Well, remember, the derivative is the slope of the tangent line. And so if we want to know the equation of the tangent line at the point 2, 2, which was our original question, we need two things, right? We need a point on the line. Great, that was given to us. Right, the point on the tangent line is the point 2, 2. And then we need the slope of the tangent line. And we know that to get the slope of the tangent line, we just need the derivative evaluated at that particular point. So our derivative y prime evaluated at the point 2, 2. This is where things get just a little bit different, because usually when we're evaluating the derivative at a particular point, we're just plugging in an x value. With implicit differentiation, you have to plug in both the x value and the y value, right? So it's a little bit different here, but it's the same idea. And in our case, we're plugging in 2 for x and 2 for y, right? Our point is 2, 2. This is our x and our y value. So we plug in 2 and 2, and we get that our slope, our y prime, is going to be equal to negative 2 over 2. The negative came from up here. Plug in 2 for x and 2 for y, and this simplifies to negative 1. Okay, now using point slope form, y minus y1 equals m times x minus x1, and plugging in my x1, my y1, and my slope of negative 1, I get the equation y minus 2 is equal to negative 1 times x minus 2. There's the equation of the tangent line for that circle at the point 2, 2. All right, we'll do a couple more examples in the next video.